So in this video, I'm going to be explaining the maximum angular velocity in which you can spin a cup or cylinder with some liquid in it until it starts spilling over the top. So when we have a normal cylinder with a liquid, it will look like this. The liquid level will be about flat, but then when we start spinning it, the liquid slowly creeps up the sides until it spills over. So there's a couple of things to assume when doing problems like this. And one is that, first of all, it's a cylinder. And the other is that this initial height of the liquid is the equivalent to this radius r. So now that we have the assumptions out of the way, we can go ahead and write the equation dP over dr equals rho of the angular velocity squared times r. So this rho is the density. This W squared is the angular velocity squared. This R is the radius. This is the dP, difference in pressure, and dr is difference in radius. So now what we can go ahead and do is multiply this dr over here. So we get dP equals rho W squared times R dr. And what we'll want to do is end up integrating that. So now what we end up getting is from 0 to big P of dP prime, and this P prime is just so we know that this P and this P are different. The rho W squared are constants, so we can take them out of the integral, and this is from 0 to big R of R dr. And what this is pretty much saying is we have our cup of liquid, this is R, and that's big R. So it's just the outermost radius. So now, if we were to solve this, we will get P equals rho W squared of R squared over 2, in which this is pressure, this is density, angular velocity squared, big R squared over 2. So now, another thing that we will need is we have our container here. In which this is when it's spinning, the liquid's creeping up the sides. What we will want is at moments, so this is 0, this is some radial point R, and this is the height at that some radial point. So now what we want is what H equals, which is this height at some radial point. So what we end up getting for that is angular velocity squared times R squared over 2g. in which this is angular velocity squared again. R is some radial point squared, and 2g, which is gravity. Well, g is gravity. The 2 is the number 2. So if we want to know what the height at this big R, the outermost radius, we would simply substitute big R into here. So we'll just end up getting W squared R squared over 2g. And this will be important later because we will substitute this in. But for now, I'm going to get rid of it. So one more thing to note is that you have your cylinder here, and your cylinder, while it's spinning, one thing to note is that the volume of liquid down here is equal to volume of liquid here. So what that means is that the volumes up here must also be equal above this line. So essentially what we have is this equals this. And that's not drawn to scale. Obviously, it doesn't look like they're equal, but they are. So now what we can do is we can say the volume of this shape, so the volume of the curvature part while it's spinning, is equal to pi r squared d, in which this is d. So it's kind of like the height of the dip. So now, if we were to integrate that, we would get r minus d plus the height of, this is the height of when the some radial point is the outermost radius itself, when that equals h, which is the height of this whole thing. So this is the cylinder. I'm trying to make this a dotted line. This is the cylinder. This is h. This is d. And this is big R. And that's 0. So again, we're saying when the height of the some radial point equals outermost radius. So now what we can do is the last equation, when we differentiate it, we'll get dv. Well, first of all, I should explain this. So if we have this angular part, the width of these bars, if we were to cut them in tiny little pieces, the width is dr. And, you know, over here is normal r. This would be the height at that point. So what we can end up doing is getting the equation dv equals h 2 pi r dr. So right here we have this little h. And if you remember earlier, we got this equation h equals w squared r squared over 2g. So what we can end up doing is plugging this h in. And what happens when we do that is we'll end up getting we'll still have the 2 pi will be easier just to do this. And we'll have the w squared over 2g and we had an r squared up here, so we can go ahead and make this r cubed dr. So now what happens is we'll want to integrate this. So the left side, the integral of dv is just v. So we'll just have v equals, and we'll have the 2 pi. Well, we can cancel out some things. So we'll have pi w squared over g and the integral of r cubed is r to the 4th over 4. So we'll have this multiplied by r to the 4th over 4. And actually, this r, since we'd be integrating from 0 to big R, it would become big R to the 4th over 4. So now what's after that? So pretty much we'll want to solve for the dip, which again was this. This is d for the dip. So now, since we had two equations that had volume, we can set them equal to each other. So what we'll end up doing is pi r squared d. This is a pi. It was a poorly written pi, which I'm just going to write this bigger. And equals the equation we just had. So we'll end up having pi w squared over g multiplied by r to the 4th over 4. So as you can see, we have 1d, which is good. And if we were to simplify these, a lot of things would cancel out, such as the pi's, some r's would cancel out. So what we'll end up getting, if we were to solve for d, is d equals w squared r squared over 4g. So this is what we'd end up getting if we simplified this equation. So now the equation we had earlier, in which it was R minus D plus H at R equals R equals big H. Now we can plug a lot of things into this. So what we'll end up getting is R minus, we're going to plug in for D. So we're going to end up getting is W squared R squared over 4G, and plus, we solved for H earlier, W squared R squared over 2G equals big H. So now what we're going to do is we're going to subtract the R from the right side to get this side alone and simplify these. So what that's going to end up doing is giving us H minus R equals W squared R squared over 2G. So now we can go ahead and try and get angular velocity on itself by itself. So what happens when we do that is we'll divide by this R squared, we'll multiply by 2G. So we are going to get W squared equals, and we're going to multiply by 2G and divide by R squared, so we're going to get 2G times H minus R divided by this R squared. So then we only have one more step left, which is to find the square root. So we're just simply going to take the square root. Actually, I just realized this earlier it should not have been 2G in the denominator, it should have been 4. So it should have been W squared R squared over 4G. That's what it should have been previously. Yeah, so it should have been this equals H minus R. Because when we take the square root, we'll get to take this 4 out and make it 2. So that's what it should have been earlier. So when we do take square root, as I said, the 4 is going to simplify out of square root and become a 2. So we are going to get, that's a little small, we are going to get 2 square root G H minus R over R. So this is our final answer, in which this is the angular velocity to its constant, G is the gravity, H is the max height. So really quick, I'm gonna, so you have this type thing, this is H, this is R. So H is the height of the whole thing, big R is the max radius, and Big R is max radius.